Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Viscous Heat Generation. So, viscous heat generation in general is important where this apparent viscosity is very high and then it is moving at a high velocity and then it is flowing in very confined narrow gaps. So, under such conditions what happens, whatever the mechanical energy is there, that converts into the thermal energy, and then because of that one heat generation takes place, and then that is known as the viscous dissipation. Okay. So, now in this lecture what we will do, we will take a few example problems where the viscous heat generation is very essential, and then in order to know how much is the temperature variation or temperature increasing because of this viscous heat dissipation, etc. Those things we are going to see by solving a few problems. Okay. Some examples of this viscous heat generation in general we see, like motor vehicles. Grease is actually confined between two cylinders, and then one of them may be rotating based on the design its requirement. So, there in general this grease is high viscous, apparent viscosity of grease is usually very high, and then these motor vehicles obviously we know that they run at very high velocities. So, and then these greases etc. are confined between very narrow spaces. So, then viscous heat generation etc. Takes place. Then the conveyors like belt conveyors, shaft conveyors etc. in general in chemical industries, where they are being conveyed because they have been confined along the two cylinders at different locations, and then these cylinders may be rotating, and then because of that one the shafts or belts may also be rotating, right. So, this cylinder is rotating, and but it is rotating. There is a inner confined cylinder which is confined, and then that is not rotating, right. So, let us say this is the inner cylinder, and then there is a outer cylinder is there. So, like this there are two cylinders are there, and then they are confined like this, right, and then this belt is moving like this. So, that the material, whatever the solid materials etc. are there, so they can be taken, poured here. So, they can be conveyed to the other locations. That is what happens. That is what happens in general, right. So, now this whatever this confined area is there here between these two cylinders. So, this is very narrow actually, this blue color maybe you can take it as a confined region. So, that is very narrow, and then that area is in general provided with some kind of high viscous lubrication fluids. So, in this phenomena what happens, this because of the high speed velocity and then high viscous fluid, the viscous dissipation takes place, that mechanical energy converts into the thermal energy, and there is a heating of the cylinders etc. takes place. So, that is also not good if it is too much heating. So, accordingly based on the temperature variation for a given speed of the rotation, and then for a given high apparent viscosity, how much temperature variation is there, those calculation one has to do. Accordingly the coolant fluid etc. may be supplied. So, that is the purpose of considering these viscous heat generation problems in general in the majority of the material or automobile kind of industry, material processing industries or automobile industries, or wherever they are applicable. Okay. So, now in this lecture we are going to take a couple of problems and then do the derivation to get the temperature distribution for these kind of geometries. So, the first instant is viscous heat generation between coaxial cylinders. This we are taking as a first problem of today's lecture. First, let us see the statement of the problem. Consider flow of an incompressible Newtonian fluid between two coaxial cylinders, where inner radius of outer cylinder is capital R. Surfaces of inner and outer cylinders are maintained at T0 and Tb respectively. Outer cylinder moves with angular velocity omega, whereas the inner cylinder remains stationary. Because of friction between adjacent fluid layers, viscous heating is being generated. In these conditions, viscous force dominate over the pressure force, that is one condition given, and then velocity profile is linear, that is also the another condition given. Width of annular space between two cylinders B is very small compared to the radius of outer cylinder capital R, so that curvature effects can be ignored, that is B is very smaller than R, so that we can avoid the curvature effects. If you are not considering the curvature effects, so even the geometry, cylindrical geometry, we can do the problem solving in Cartesian coordinate system. Okay, that we see now. And then the statement is problem statement is schematically represent the aforementioned problem statement and obtain temperature profile within the annular space between two cylinders. So, first schematically we represent this flow problem, and then we get into the solution steps to get the temperature profile. So, now schematically if you see, this is the inner cylinder whose radius is not known, not required also for this problem, is maintained at temperature T naught, and then this is the outer cylinder whose radius is capital R, and then it is maintained at temperature T b. The gap between these two cylinders is B, and then B is very smaller than R, so that we can avoid the curvature effects, and then this outer cylinder is rotating with angular velocity omega, right. So, now since B is very small, smaller than the radius of outer cylinder capital R, what we can say, curvature effect is negligible, and then that is given in the problem statement as well. So, now this problem we can represent in Cartesian coordinate system. So, how we can do, you just cut this cylinder at any location and then stretch it. Then what you get, you have a geometry like this, where the surface of inner cylinder is x naught, surface of inner cylinder, which you can designate at x is equals to 0, and then top layer is surface of outer cylinder, right, which is moving at velocity omega. So, if this velocity, if you convert into the rectilinear coordinates velocity component, then you get r omega as that velocity, and then let us designate r omega as V b, right. The gap between these two cylinders is small b, inner cylinder is at T naught temperature, outer cylinder is at T b temperature, the velocity profile is linear, right. So, that is also given V z, and it is function of x only. The temperature is function of x, right. The nature of temperature profile we do not know what it is, right. So, that is what we are going to find out, okay. But nature of the velocity profile is given, it is linear. So, we have to find out what is the slope intercept of this linear profile, that we have to do, okay. So, since we have two boundary condition at x is equals to 0, V z is equals to 0, and then at x is equals to b, V z is equals to V b or r omega, right. So, we can find out those constants anyway, okay. So, this is the schematic representation of the problem. The temperature profile whatever is shown here, it is just a representation it is shown, it is not the true nature of the curve, that we have to find out. So, limitations of this problem if you list out, V z velocity is only existing and then it is function of x, temperature is function of x only, so that is T is function of x only, steady state and incompressible flow, constant physical properties, and then curvature effect negligible. So, Cartesian coordinates can be applied, okay. The fluid nature is Newtonian fluid, it is not given any fluid. So, then we can take a Newtonian fluid, okay. So, it is given that velocity profile is linear in the problem statement, that means V z is some constant x plus another constant, that is what we have. We can have that linear profile like this. So, what is C1, C2 we find out. At x is equals to 0, V z is 0, so C2 is equals to 0 you will get. at x is equals to b, Vz is equals to Vb. So, Vb is equals to C1b plus C2. So, C1b is nothing but Vb by b, because C2 is 0, right. Now, C2 is known, C1 is known. If you substitute them here in this velocity profile, Vz is equals to Vb by b is C1 multiplied by x plus C2 is 0. So, linear velocity profile that is given, which is having this form. The linearity on the constant Vb by v is the slope, right, and then there is no intercept. Okay. So, this is the velocity profile is given. What if it is not given, or what if you are not sure from the problem statement whether the velocity profile is linear or not? Then what we have to do? We have to follow the conventional step of simplifying the continuity equation and then momentum equations, getting an expression for the shear stress, and then substituting corresponding expression for the shear stress as per the rheology of the fluid, then integrating it and getting the velocity profile. That is what we have to do, right. So, as a practice we do that one also, though it is given. So, continuity equation in Cartesian coordinates is given, this one. Steady state, this term is 0, Vx, Vy are not existing, Vz is existing, but it is not function of z, it is function of x only. So, continuity is satisfied. So, the constraints are whatever the constraints that we have listed, they are reliable ones. Then equation of motion in Cartesian coordinates, x component of equation of motion in Cartesian coordinates if you write. So, this is what we have. We have written for the Newtonian fluid directly, we have written for the Newtonian fluid. So, then it is a Navier-Stokes equation. Okay. So, Navier-Stokes equation x component is given here. Steady state, this term is 0, Vx is not existing, Vy is not existing, Vz is existing, but Vx is not there. So, this term is also 0. In general, pressure we do not know what is the function. Vx is 0. So, all these 3 terms Vx are there. So, then all that viscous force term is 0. Then gravity we are not taking, horizontal configuration we are taking. So, what we get? Dou p by dou x is equals to 0, that means pressure is not function of x. Similarly, y component equation of motion or Navier-Stokes equation for Newtonian fluid is given here. Steady state, so this term is 0, Vx is not there, Vy is not there, Vz is existing, but Vy is not there. So, here also left hand side all terms are negligible. Pressure in general we do not have any information. Vy is 0, so all these 3 terms again here viscous force terms are 0. Then gravity we are not taking here, horizontal configuration. So, here also we get dou p by dou y is equals to 0, that means pressure is not function of y, right. Next, z component of equation of motion in Cartesian coordinates for a Newtonian fluid if you write. So, that is this equation. So, steady state this is 0, Vx is 0, Vy is 0, Vz is existing, but Vz is not function of z, it is function of x only. So, this term is 0. So, that way also left hand side term, all the terms here also 0, negligible. Pressure in general we do not know what it is. Vz is existing and then it is function of x. So, we cannot cancel out this term. Vz is existing, but it is not function of y and z. So, these 2 terms are 0. Gravity we are not having any term here. So, what we get here, dou p by dou z is equals to mu dou square Vz by dou x square. But in the problem statement it is given in this viscous dissipation problems, in general the viscous forces are very strong compared to the pressure and other forces. So, we can in comparison to these viscous forces, the pressure forces are small. So, then we can strike out. So, that is given in the statement also, in the problem statement, pressure is very small and negligible compared to the viscous forces. That means, we have mu dou square Vz by dou x square is equals to 0, that means Vz is equals to C1x plus C2 and then same constant. Now, once after this the constants obtaining is same, like whatever we have done by assuming this velocity profile directly. So, then same constant we get C2 is equals to 0 and then C1 is equals to Vb by b you get when you apply the boundary conditions, then you get Vz is equals to Vb by b x, same velocity profile we are getting. Okay. So, however, for this problem this step was not required because it is already given, but as a practice we are doing it. Now, energy equation we have to simplify. Energy equation in Cartesian coordinates is given this one, rho Cp dou t by dou t plus Vx dou t by dou x plus Vy dou t by dou y plus Vz dou t by dou z is equals to k dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus mu phi v. This mu phi v is nothing but viscous dissipation term, right. It is having 9 terms, right. So, that we are going to write in the next step. So, in general when you write the energy equation, we take only this temporal term and then convection term and then conduction terms only. Other terms as per the requirement of the problem, reaction terms, viscous dissipation, etc., whatever are there. If specific to the problem, then only we write, otherwise we do not write. So, now specific to this problem, viscous dissipation term should be included. So, that term is this one. So, we expand this one in the next step. Before that, we simplify this equation. Steady state, so this term is 0, Vx is 0, Vy is 0, Vz is not 0, it is there. Temperature is not function of z, it is function of x only, it is given. So, left hand side here also all the terms are 0, and then temperature is function of x only, it is said. So, then this term should be there, it is not function of y and z. So, these two terms are negligible. So, then what we get, minus k dou square t by dou x square is equals to mu phi v, and now we expand phi, now if we expand phi v, we get this expression, this entire expression from here to here. This is the viscous dissipation term. Now, here also we have to apply the constraints. So, limitations, that is the reason we have written at the beginning of the solution. Limitations we have not only written just for the temperature purpose, we also written for the flow point of view also, because the flow is also associated and then that is being affected because of this temperature profile in general. Okay, our temperature profile is being affected by the flow phenomena. So, that is the reason now we are that is the reason we have listed the constraints associated with the flow. So, that those constraints would be helpful now to simplify this phi v term, right. So, Vx is 0, this term is 0, Vy is 0, this is 0, Vz is there, but Vz is not function of z, it is function of x only. So, this term is also 0, Vx is 0, Vy is 0, Vz is there, but Vz is function of x only, it is not function of y. So, this term is 0, Vy is not there, so this is 0, Vx is not there, this is 0, Vz is existing, right, and then it is function of x also. So, this term should be taken. So, this term would be there, right. So, from here Vx is 0, Vy is 0, and then Vz is function of x only, it is not function of z. So, what we get here, phi v is nothing but just dou Vz by dou x whole square. That means minus k dou square t by dou x square is equals to mu dou Vz by dou x whole square. But Vz what we have, Vz is equals to Vb by b x. So, dou Vz by dou x is Vb by b. So, mu Vb by b whole square, this is what we are having. Now, this minus k also we take it to the right hand side. So, dou square t by dou x square is equals to minus mu by k Vb by b whole square. So, if you integrate it, dou t by dou x is equals to minus mu by k Vb by b whole square x plus C1. If you integrate it again, t is equals to minus mu by k Vb by b whole square x square by 2 plus C1x plus C2, right. So, this is the temperature profile, but it is having two unknowns C1, C2. So, those two unknowns now we will be finding out using the boundary conditions. What are the boundary conditions? At x is equals to 0, t is equals to t naught, at x is equals to b, t is equals to tb, they are given. So, when you substitute at x is equals to 0, t is equals to t naught, then we have right hand side 0 plus C2, that is C2 is equals to t naught. Other boundary condition, at x is equals to b, t is equals to tb is equals to minus mu by k Vb by b whole square. In place of b, in place of x square by 2, now you have b square by 2 plus C, in place of C1x you have C1b plus C2. C2 you already got it as T naught. So, this is T naught. Now, this T naught we take to the left hand side. So, that Tb minus T naught is equals to minus mu by k Vb square 1 by 2 plus C1b, because this b square can be cancelled out. So, from here C1 we get it as 1 by b Tb minus T naught plus mu by k Vb square by 2. So, this is C1. Now, this C1 and this C2 both we substitute here in this equation and then simplify to get the required temperature profile. So, this is what we have substituted. The first term is irrespective of the constant. So, that is as it is. C1x is nothing but 1 by b Tb minus T naught plus mu by k Vb square by 2 multiplied by x. So, x by b we have written plus C2 is nothing but T naught. So, now this is the final temperature profile, but however what we do some more simplification so that we can have this equation in simpler form. So, now this T naught will take to the left hand side. So, we have T minus T naught and then both the sides we are dividing by Tb minus T naught. So, in the first term as it is and then divided by Tb minus T naught. Second term x by b, this term if you divide by Tb minus T naught. So, here 1 and then here you get second term you get Tb minus T naught. T naught we already taken to the left hand side before dividing by Tb minus T naught. Okay. So, now what we do, this term if you expand, this is x by b plus x by b mu Vb square by 2k 1 by Tb minus T naught, this is what we are having. So, now what we do, this term and then this term, from these two terms we will be taking this mu b square by 2k Tb minus T naught as common. So, x by b also we are taking common. So, now this is this term we are taking common. So, this multiplied by 1 minus x by b, from this term the same thing if you take common x by b, another x by b would be remaining from this term, right, and then this x by b is as it is, right. So, now this term T minus T naught by Tb minus T naught is equals to x by b plus 1 by 2, this entire term whatever is there, that I am calling it Br, x by b multiplied by 1 minus x by b. This is the final temperature profile in a simplified manner, because we know that T is function of x only, all other constants whatever are there. So, they are grouped as mu Vb square by k Tb minus T naught, which is nothing but Brinkman number, right. So, this is how we can obtain the temperature profile in the case of a viscous dissipation problem. Now, the same problem becomes complicated if curvature effects are not negligible. This problem we are going to take in subsequent lectures. So, but the same problem, exactly same thing, but only additional thing that if you say that if the curvature effect is not negligible, so then mathematically simplifying these equations, the process steps are same, right, but only thing that you will be solving in cylindrical coordinates when the curvature effects are not negligible. Then under such conditions mathematical simplifications becomes little tough. So, those problems we take in subsequent lectures anyway. Now, this we have taken if the fluid is Newtonian fluid, but primarily our purpose is to see such kind of problems, especially when the fluid is obeying some kind of non-Newtonian rheology, right. So, now the same problem we will revisit, but now the fluid we take a power law fluid. Okay. So, viscous heat generation in coaxial cylinders due to motion of power law fluids, all conditions are same, everything is same, only thing that the fluid is power law fluid. The velocity profile can be obtained by simplifying the equation of motion, and all those steps we can follow, because let us assume in this case we are not sure whether the profile is linear or not, because the fluid rheology's power law behavior is non-linear. So, we are not sure, even if the confinement, the gap between two cylinders is very small, whether the velocity profile is going to be linear or not, we are not sure if the fluid is obeying non-linear, non-Newtonian behavior such like power law fluids or something else like that. So, that is the reason we follow the standard steps to obtain the velocity profile as well. Okay. So, now what we do? See, the same equations of continuity and then motion we will be writing in Cartesian coordinates and then applying the constraints to get the velocity profile. Okay. So, continuity equation is given here, steady state this term is 0, Vx is 0, Vy is 0, Vz is not function of z, it is function of x only. So, this term is also 0, that means continuity is satisfied. Then equation of motion in Cartesian coordinates, x component is given here. So, now here the difference you can see, the viscous terms have been provided in terms of the extra stress component tau xx, tau yx and tau zx, etc. It is not given directly in terms of velocity, because tau will be substituting later on once simplifying this equation based on the nature of the rheology, right. The nature of the rheology is simpler in the case of Newtonian fluid. So, that directly you substitute here and then simplify. So, then directly you get plus mu dou square Vx by dou x square plus dou square Vx by dou y square plus dou square Vy plus dou square Vx by Vz square, that is what directly you get on this step. But here now in this case of power law fluid, this tau expression is complicated, non-linear. So, when you substitute here it becomes very complicated. So, that is the reason we substitute it later. And then here Vz is function of x and then only tau xz component is only existing, which is function of z. Temperature is anyway function of x. So, these constraints we apply and then simplify now. Steady state, this is 0, Vx is 0, Vy is 0, Vz is existing, but Vx is not there. So, left hand side altogether again 0, we do not know. So, this is having, all this is having like Vx terms. So, this is 0, here Vx, Vy terms only be there. So, this is also 0, here Vz term will also be there, but Vz is not function of z, it is function of x. So, then this term is also 0, then there is no gravity. So, this term is also 0. So, we get dou p by dou x is equals to 0, that means pressure is not function of x here again. Now, y component of equation of motion for a non-Newtonian fluid, if you write in Cartesian coordinates, this is that equation. So, steady state, this term is 0, Vx is not existing, Vy is not existing, Vz is existing, but Vy is not existing. Pressure terms we do not know, so let us leave them as it is. Here from tau xy terms, if you expand you will have Vx, Vy terms. So, then this is 0, only tau zx or tau xz is existing, tau yy is not existing, tau zy is also not existing. Okay. So, that is 0 and then gravity is not there. So, here also we get dou p by dou y is equals to 0. So, the pressure is not function of y again. Z component of equation of motion in Cartesian coordinates for a non-Newtonian fluid, if you write, this is what you have. So, steady state, this is 0, Vx is not there, Vy is not there, Vz is there, but Vz is not function of z. So, this term is also 0. Pressure we do not know, right. Tau xz is existing and then it is function of x. So, we cannot cancel out, it should be there. Tau yz is not existing, tau zz is not existing, the gravity is not existing because of horizontal configuration we are taking. So, here dou p by dou z is equals to minus dou tau xz by dou x you are getting, right. Now, here in place of tau xz you substitute minus m dou vz by dou x power n and then substitute it and then simplify to get the required velocity profile. But before doing that one, so this is a viscous force term, right, and this is pressure force term, right. So, in this problem, viscous heat generation problem, in general viscous forces are very strong compared to the other one, and then pressure force is very small and negligible compared to the viscous forces. So, this term can be cancelled out. So, we have only dou by dou x of tau xz is equals to 0, right. Now, tau xz is equals to C1 on integration and then tau xz we can have minus m dou vz by dou x power n is equals to C1. Now, you take this C1 and you take minus m to the right hand side, so that C1 by m, and then both sides you do whole power 1 by n. So, then you get dou Vz by dou x is equals to minus C1 by m whole power 1 by n. Now, you integrate this one, Vz is equals to minus C1 by m whole power 1 by n x plus C2. So, here also before obtaining this constant C1 C2, we can understand in the case of power law fluids also the velocity profile is linear. Only thing that constants we have to obtain. Let us see if the constants are also same or not. After obtaining the constants, are we getting the same velocity profile as in the case of Newtonian fluid or not, that we check. So, at x is equals to 0, Vz is 0. So, C2 you are getting 0, that means Vz is equals to minus C1 by m whole power 1 by n x, right. C2 is 0 anyway. Now, apply the second boundary condition at x is equals to b, Vz is equals to Vb, and then that should be equals to minus C1 by m whole power 1 by n b in place of x, right. So, now you can rearrange this one as C1 minus C1 by m is nothing but Vb by b whole power n. So, now in place of this one, in place of minus C1 by m, you write Vb by b whole power n, and then this whole power 1 by n is there x. So, Vz is equals to Vb by b x. Here also you are getting linear profile, and then profile is exactly same as in the case of Newtonian fluid. What does it mean by? It means like, if the fluid is Newtonian or power law fluid, the confinement is very narrow, then the velocity profile is going to be linear in either of the case. But it does not mean that the temperature profile is also going to be same. Definitely it is going to be different, and then how different it is, that we are going to derive now. So, generalized equation of change for energy that we have derived in week number 3 or 4 previously. There what we derived generalized energy equation is this one, dou by dou t of rho v square plus rho u tilde is equals to minus del dot t plus rho v dot g, right. So, this is the generalized one. Then after that we have done several simplification, and then the same energy equation we obtain in 4-5 different forms of energy, and finally we got energy equation in the form of temperature. Okay. So, now this equation we are going to use here, right. Here E is nothing but this one. So, this term indicates the convection term, this indicates the both pressure and then molecular forces terms. Molecular forces terms are also including the viscous dissipation terms, etc., and then this term indicates the conduction term, right. And then this E, how many components are there? It is having Ex, Ey, Ez, 3 components we are having. So, if you expand this one, you get the 9 such components. Okay. This phi we know as P delta plus tau, and then finally this is also we have seen E is equals to half rho v square plus rho h tilde v plus tau dot v plus q. This is what we had seen, right. So, this we are going to simplify for given problem, because the energy equation now directly in the temperature form we cannot write. Why we cannot write? Because in that form, the viscous dissipation term whatever is there, that is not for power law fluids, it may be different way. For non-Newtonian fluid it is incorporated in a different way. So, how different, that we can understand from here only, because this term is going to play leading role now because of non-Newtonian rheology, and this is directly not available in energy equation in the form of temperature. So, the same equation is written here also. So, now what we understand, we are taking only, see this E is having Ex, Ey, Ez, that means energy changes, it is there as function of x only. So, whatever the Ey terms, Ez terms are there, so that are all having function of y, z, something like that. So, then altogether we can cancel it, we do not need to expand that, we do not need to worry about Ey, Ez terms at all, right. So, we take only x component of this E, x component of E if you see. So, this is going to be Vx, and then Vx component is 0. So, that means this term is 0 altogether, right. And then this q, only conduction minus k dou t by dou x term would be there. In the q also you have qx, qy, qz terms, only qx term is there, and then that is minus k dou t by dou x, only that term is required. And then tau dot v, its x component, if you see, it is tau xx Vx plus tau xy Vy plus tau xz Vz. This is also we have seen previously, right. So, now Vx is 0, Vy is 0, Vz is there, and then tau xz is also there. So, tau xz Vz. So, this term is going to give you the contribution of viscous dissipation in the change of temperatures. So, that is the reason this is how we are doing for the power law fluid, right. Now, so finally E x, so the same equation, when you simplify by using these 3 constraints, E x component only if you take, so E x is equals to q x plus tau x z V z, q x is nothing but minus k dou t by dou x. So, this is the one, right. Now, energy equation, equation number 5 in the generalized form, this is what we had, right. So, this now we have to simplify as per the constraints of the problem. So, steady state, so this term is 0 altogether, and then we are not taking gravity. So, this term all the terms would be having gravity. So, altogether we can cancel out. Even after expansion, each and every term associated with this one is having gravity g term. So, we can cancel out altogether. So, what we get, del dot E is equals to 0, and then del dot E, if you expand, it is dou E x by dou x plus dou E y by dou y plus dou E z by dou z is equals to 0, and then E x is there only in the x direction, temperature variations are there. So, E x is existing and it is function of x. So, then we cannot cancel out, it would be there, but E y is not there, and then it is not function of y also. E z is not there and it is not function of z also. So, E x dou E x by dou x is equals to 0, that means E x is equals to C1. And then what is this E x? In the previous slide we derived it as minus k dou t by dou x plus V z tau x z. So, this should be equals to C1. Now, this is the final expression, final simplified expression for the viscous dissipation due to the power law fluid. So, this equation now you can solve, right. Only thing that here in place of tau x z you have to substitute minus dou V z by dou x power n. So, that when you write this equation you have, right. Now, dou V z by dou x is nothing but V b by b, because V z is equals to V b by b multiplied by x. So, dou V z by dou x is going to be V b by b. So, here in place of dou V z by dou x we can write V b by b whole power n. So, minus k dou t by dou x is equals to C1 plus m V b by b whole power n V b by b x. This V b by b x is coming because of V z term, and then this is coming because of dou V z by dou x term. So, m x V b by b whole power n plus 1 we should have. So, that is when you take this minus k of left hand side also in the right hand side, k dou t by dou x is equals to minus C1 minus m V b by b whole power n plus 1 multiplied by x. Now, you integrate this equation both sides, then you get k t is equals to minus C1 x minus m x square by 2 V b by b whole power n plus 1 plus C2, this is what you get, right. Now, this equation we are going to obtain the constant C1 C2. So, now this equation we have to obtain constant C1 C2 by applying the boundary conditions for the temperature. Okay. So, at x is equals to 0, t is equals to t naught. So, that means k t naught is equals to 0 plus C2, that means C2 is equals to k t naught, and then x is equals to b, t is equals to t b, that means k t b is equals to minus C1 b minus m b square by 2 V b by b whole power n plus 1 plus C2 is k t naught. right. So, now what we do, this k T naught we take to the left hand side, and then this m b square by 2 v b by b whole power n plus 1 also we are taking to the left hand side. So, here it is, we are not expanding or cancelling b terms etcetera, that not required. So, minus C 1 b is this one. So, C 1 is nothing but minus k by b T b minus T naught minus m b by 2 v b by b whole power n plus 1, right. So, now this C 2 and this C 1 we are going to substitute in this equation number 10 to get the final temperature profile. So, this is C 2 k T naught, and this is the minus m x square by 2 v b by b whole power n plus 1 term is as it is, and then minus C 1 x is nothing but k b by b T b minus T naught multiplied by x plus m b by 2 v b by b whole power n plus 1 multiplied by x. Now, this k T naught we take to the left hand side. So, k T minus T naught is equals to k T b minus T naught x by b plus m b square by 2 v b by b whole power n plus 1. What we are doing from these two terms? We are taking m b square by 2 v b by b whole power n plus 1. So, that the first term will be having x by b, and then from this second term we have we will be having minus x square by b square. So, this is what we are having. So, in the next step what we do? We divide by T b minus T naught and k both sides. So, that left hand side we have T minus T naught by T b minus T naught is equals to x by b plus 1 by 2 m b square v b by b whole power n plus 1 as it is, and then dividing by T b minus T naught k, and then multiplied by x by b minus x by b whole square as it is. So, now here this equation we can write T minus T naught by T b minus T naught is equals to x by b plus 1 by 2, whatever the term that is there within the parenthesis, this we are calling b r n, and then from these two terms we are taking x by b common. So, multiplied by 1 minus x by b we are having. So, now here this b r n is nothing but Brinkman number for the case of power law fluids. Fine. So, if the fluid is obeying non-Newtonian behavior, so simplifying the generalized energy equation and then getting things done is more appropriate, especially if the molecular forces are contributing some changes in the temperature profile, like in viscous dissipation. Okay. Now, before winding up the class, we take one more similar case, okay, that is viscous heat generation in slit flow. So, here the statement is find temperature profile for viscous heating problem shown in below figure with given boundary conditions at x is equals to 0, T is equals to T naught, at x is equals to b, q x is equals to 0. So, now the figure is given like this. So, only thing that the boundary condition is same compared to the problem 1. This is, let us say, if you take problem 3 of the class, problem 1 where we have taken like viscous heat generation between coaxial cylinders by avoiding the curvature effects. So, then we had T is equals to T b at x is equals to b. Now, in place of that one we are having constant flux, 0 flux case we are having, that is q x is equals to 0, that boundary condition we are having. So, then how the temperature profile will change, that we will see now. Here again bottom surface is stationary, top surface is moving with constant velocity v b, and then velocity profile between these two surfaces is linear, and then that is function of x, right. The gap between these two is b. Temperature of bottom stationary surface is T naught, and then boundary condition for the top moving surface is q x is equals to 0. So, what is T as function of x, that is what we have to find. Only difference is that this boundary condition is only difference compared to the problem that we have seen previously. So, assumptions, constraints of the problem: steady incompressible flow nature of the fluid is not given. So, by default we should take Newtonian fluid. Constant physical properties Cp, rho, mu etc. are constant. Only Vz is existing and it is function of x. Temperature is function of x only, that is T is function of x. Velocity profile is linear given in the figure. So, we can have Vz is equals to C1x plus C2. If it is not given, then we have to simplify the equation of motion and get the required velocity profile applying the boundary conditions available for the velocity, right. So, now it is given in the profile, in the picture it is given that velocity profile is linear. So, then we can take this one. Now, the constant C1, C2 we have to obtain. So, at x is equals to 0, Vz is equals to 0. So, C2 is equals to 0. At x is equals to b, Vz is equals to Vb. So, C1b plus C2, C2 is 0. So, C1 is equals to Vb by b. So, that means here also we are getting same velocity profile, Vz is equals to Vb by b x. So, even if the boundary condition of the moving surface has been changed for temperature, the velocity profile is not being affected. So, that means what does it mean by these problems? The velocity profile is affecting the temperature profile, but temperature profile change in temperature, non-isothermality in the system, that is not affecting the velocity profile. Neither the rheology of the fluid is affecting the velocity profile, because the narrow gap it is having and all that, right. So, because of the flow, temperature profile is changing, that we are measuring now. So, energy equation, this is what we have in Cartesian coordinates. Steady state, this term is 0, Vx is 0, Vy is 0, Vz is existing, but temperature is not function of z, it is function of x, that is also given in the problem statement. Conduction or heat changes are existing in the x direction. So, this would be there. These two Qy, Qz are not existing and they are also not function of z, and then viscous dissipation, this term should be there. So, what we get? 0 is equals to minus dou by dou x of, in place of Qx we are writing minus k dou T by dou x mu multiplied by, in place of phi v viscous dissipation term, this is what this we have. So, now here again we apply the constraints of the flow, to further simplify this equation. So, Vx is 0, Vy is 0, Vz is there, but it is not function of z. So, first three terms are 0, Vz is there, but it is not function of y. This term should be dou Vy by dou x, right, dou Vy by dou x. So, Vy, so there is a typo here. So, it should be dou Vy by dou x. So, here this Vy is 0, Vx is also 0, Vz is existing, but it is not function of y. So, it is 0, Vy is 0, Vx is not existing, Vz is existing and it is function of x. So, this term would be there. Vx is 0, Vy is 0, but Vz is existing, but it is not function of z. So, this term is also 0. So, here also we get dou by dou x of minus k dou T by dou x is equals to mu. Out of these terms only one term dou Vz by dou x is remaining. So, dou Vz by dou x is nothing but Vb by b from the velocity profile. So, mu Vb by b whole square. So, this equation now what we do? We integrate it. When you integrate first time, minus k dou T by dou x is equals to mu Vb by b whole square x plus C1. Then what we do? We take this minus k to the right hand side, then we have dou T by dou x is equals to minus mu by k Vb by b whole square x minus C1 by k. On integration, T is equals to minus mu by k Vb by b whole square x square by 2 minus C1 by k x plus C2. Now, the first boundary condition at x is equals to 0, T is equals to T naught. So, 0 minus 0 plus C2, that is C2 is equals to T naught. Another boundary condition at x is equals to b, Qx is equals to 0, Qx is nothing but minus k dou T by dou x. So, that means dou T by dou x is equals to 0, and then from equation number 2 we had dou T by dou x is equals to minus mu by k Vb by b whole square x minus C1 by k. So, here now what we substitute, x is equals to b we substitute and then equate the left hand side term to 0. Then we have 0 is equals to minus mu by k Vb by b whole square b minus C1 by k. So, C1 by k is equals to minus mu by k Vb square by b. So, C1 is equals to minus mu Vb square by b. So, this C1 and then C2 is equals to T naught, these two we are going to substitute in this equation number 3 which we have derived previously. So, in place of C1 you can write minus mu Vb square by b, then we have this is the second term, that is plus mu Vb square by kb x, and in place of C2 you can write T naught, the first term is as it is. So, this T naught you take to the left hand side and then right hand side terms you take common mu Vb square by k, then you have x by b minus 1 by 2 x by b whole square. So, that is T minus T naught by mu b square by k is equals to x b minus 1 by 2 x by b whole square. This is the temperature profile for a viscous heat generation in a slit flow where Qx is equals to 0 at moving surface and T is equals to T naught at stationary surface at x is equals to 0, moving surface is at x is equals to b. The form wise it looks similar, but the profile is different compared to the case where T is equals to Tb at moving surface, that is at x is equals to b. The reference, these problems can be found from this standard book. Other references are also provided here. Thank you.